No. Okay, we are live. Hello, everyone. I'm Erica, and I'm here with Ken Wolgemuth today. Some of you may know, some of you may know Ken from his book, one of the books that he's an author, Grand Canyon Monument to an Ancient Earth. Yep, there it is. My copy is actually sitting in the kitchen. I was rereading your chapters to prepare for this. So I have the utmost pleasure of having Ken here today. We're going to be talking about a lot of stuff. We'll go ahead and let Ken introduce himself, and then before we jump right into things, I'll kind of let everyone know what the format for today is, because it's a little different than normal, and I'm really excited for it. So Ken, tell us a little bit about who you are, what you do, and then toss it back to me, and we'll get started.
Okay, thank you very much. I was thrilled to be able to hear Erica about 2-3 weeks ago with a friend of mine, Jonathan Baker, and that caught my attention. And so I got the email address somehow, and I emailed her, and so we got connected. And turns out we don't live too far apart, just about 2 hours away from each other. So that was a surprise. I grew up in central Pennsylvania, and my dad was a chemistry professor at a small college there. It's a Christian liberal arts college. So in my growing up pattern in that small community, I have known and recognized God as my creator from as young as I could remember, as long back, so that's the environment that I grew up in. It was a very, it was just a wonderful kind of setting because things were all safe in the community back in those days. A lot of the stuff that influences communities today was not in our community. So it was one of my cousins, in fact, he said, when we got together for the 100th birthday of one of my aunts, she said, Ken, we just really grew up in an idealized environment here where we were here outside Harrisburg, Pennsylvania. I said, yes, I know. It's absolutely true.
Yeah.
Anyway, my dad was in chemistry, and I learned that I also ended up enjoying chemistry. So I went through high school locally there, and then I spent 2 years at the college where he was a professor, and I had, in fact, Dad for my chemistry. So that was an interesting mix, of course, as it happened. But it worked out okay. And then I transferred from Messiah College there in Pennsylvania out to Wheaton College in Illinois. And at that step, then I finished a bachelor's degree in chemistry there out at Wheaton in Illinois. As I was thinking about potential of graduate school, my department chairman there, an advisor, said, well, why don't you consider geochemistry? And I had to ask him, well, what's that? He said, well, taking chemistry and using it to study the earth and God's creation. And that sounded interesting, but I wasn't prepared to jump straight into graduate school immediately. So after I had my BS in chemistry, I went out to the Black Hills to a science station there, and I had my first course in geology. And this was crazy. Like, I was in blue jeans and t-shirt and hiking boots and getting college credit for it. So that really caught my attention. So I did it. Course. Oh yeah, it was unbelievable. And that was a good place. The Black Hills are an excellent place because they're igneous rocks in the core that have Mount Rushmore, and then there are sedimentary rocks of the Paleozoic and Mesozoic out toward the east of the Badlands there.
Yeah,
we weren't far also from Devil's Tower, so we were able to take field trips over there to see that kind of a volcanic rock. So
yeah.
So then I ended up getting into graduate school. My graduate school work in geochemistry was at Columbia University in New York City. And within a year of arriving there, my advisor put me on an oceanographic research vessel in Victoria, British Columbia. And I sailed down into the Pacific, in the South Pacific. And then eventually, over 2 or 3 months legs, I came back through the Panama Canal and returned back to New York City.
Right.
And it was so crazy to think of me that, this semi-country boy from central Pennsylvania getting to the South Pacific and Tahiti. That was pretty heady stuff for me as whatever I was, 23, 24, 25 at that point, something like that. So I did my thesis work in ocean chemistry. So all those trips, those kind of trips, I was collecting water samples to do chemistry work. Once I finished my PhD, I taught at Dickinson College in geology for 5 years. My wife and I went to Brazil, and I spent 2 years down there teaching in graduate school as a visiting professor of geochemistry. When I returned to the United States, then I made a transition into the oil industry. First in Salt Lake City, Utah, where there was a specialized laboratory for analyzing rock samples for the oil industry. Then I moved to Tulsa, Oklahoma, where I'm still living, to work for the Hess Corporation, which was an oil field operating company. So I've been in the oil industry now for 35 years, with working for them, working for the American Association of Petroleum Geologists, and now for the last 25 years, teaching contract courses for a big oil field service company named Schlumberger, and they've sent me around the world teaching petroleum engineering and petrophysics to geologists and engineers in oil companies.
Right.
And then I also have a class that's a 2-day class that's designed for people that work in oil companies and wonder what in the world those crazy geologists are doing in their offices with those big sheets of paper with squiggly lines on them.
Right.
And so teaching that class. So that's been my effort then for the last 20 years. About 15 years ago, I got drawn into the church community related to science because they became aware of the division and a significant amount of disinformation is being spread around in the church by the young earth creation community. And I just felt drawn to seeking to try to communicate effectively what I find in geology and geochemistry as trained and as being a Christian in the church community. So I have a rapport when I am able to speak in a church or a seminary or to homeschool environments. So that's sort of a capsule of my history and getting involved now in speaking at churches and to seminary and church people. So back to you, Eric.
Man, I don't think that there's anyone more to do so than someone who's had such extensive geology experience and geochemistry experience as well. As someone who's not involved in geology, it blew me away when I first started digging into it on just how much we can figure out with regard to paleo environments based just on the chemistry. The chemistry alone, from things like isotopic ratios to which particular chemicals are present, giving us clues, the temperature and kind of flora and fauna would have been able to inhabit the area. It blew my mind. And before we went live, we were talking a little bit about how it's kind of like looking at a crime scene. It's a forensics, right? Piecing together the past using the present. And I think it's one of the things I loved about Grand Canyon Monument to an Ancient Earth is the joint effort between Christians and secular folks alike who are coming together and saying, look how awesome this beautiful wonder of the world is in the Grand Canyon. And I wholeheartedly agree that, there's nothing from my perspective, of course, that prevents folks who have a great relationship with God, of faith, and things like that to do awesome, incredible science. Some of the best scientists we've ever had have been Christians. And it boils my blood when young earth creationists come in and they're like, actually, we're going to go ahead and just sweep all that science under the rug and do it this way. So I was pleased when I got your email because the first thing I thought was, holy cow, you were in my side chat. And I was like, oh, Ken, I know Ken. So I'm so glad to have you here. And I'm very, very excited for your presentation and also for the presentation. So for those of you who are in the audience, we've got about 32-ish, 34-ish people who are watching right now. It'll probably continue to go up as people filter in. I wanted to let everyone know the format for today because Ken will give us a presentation. And periodically throughout the presentation, you're going to have the opportunity to kind of pick his brain a little. And I know I'll be doing that. So if you have any questions, put them in the side chat and tag me at Gibbon, and then I'll ask Ken when we kind of have those natural breaks. We have about an hour for the presentation, and then we're going to just do an open conversation, and that's going to be another opportunity for you guys in the side chat to ask Ken any questions that you want. This is a superb opportunity because, as you just heard, golly, he's got a lot of experience in geology. So that's kind of what we're going to do today. And we're just going to kind of jump into it. So Ken, go ahead and share your screen. And when you do, we'll pop that bad boy on the monitor so that everyone can see it and just get right into it.
Okay. Let me get my screen shared. Go. Share screen.
Just waiting on the pop-up.
Share screen. And now finding PowerPoint. There we go. All right. Does that show up the Grand Canyon pretty nicely?
We don't have it just yet. Did you click the...
Just a few moments. Do I have to do something?
I think because it showed the first two times when we were doing this beforehand. So you just want to click share at the bottom.
Did I
share screen?
Share quite correctly? It says
yeah, I think so. I think maybe
share again.
Yeah. So click. Yeah. So you have to click that. You have to click your entire screen in the center, and then it should say click. You should have a share option kind of at the bottom.
Oh, there's one.
Ah, there it is. Cool. Okay. Yeah, there we go. We got it.
Okay.
Yeah, sure can.
Evidence for an ancient Earth. Is that what's on the screen?
Oh, yeah. We can see it loud and clear.
My only disappointment with this picture is that's not me out there in those rocks. I wish it were, but that's not the case.
For the sake of argument, we'll just assume it is.
Yeah, we'll pretend for this time. That Solid Rock Lectures at the bottom corner is a nonprofit that I set up so that some colleagues and I could be, in fact, going to seminaries, and we'd have a suitable name to use to promote being able to give lectures and workshops at church type of environments. So that's where that comes from. I do use the word creation a lot because I'm always speaking to people that are in the church setting. So I'm thinking of my presentation here is that I'm talking about creation story. And we indeed have an ancient Earth. And for those of us in the church community, we are persuaded that we have a magnificent creator. Let me get the pointer on there. I love this volcano because it shows a little puff there at the top. And in the Bible, in the Psalms 104, the book reads, he touches the mountains and they smoke. So I'm an individual that I see God as active in his creation on a regular basis. He invites us to study the earth, which has been my privilege now for half a century. Or from Job, speak to the earth and it will teach you, or let the fish of the sea inform you. So that's what we do in the sciences of geology and biology and chemistry and physics. One of the greats of science from past centuries, Johannes Kepler, who was looking at the motion of the planets in the solar system, made this comment as he viewed all science investigations, that the chief aim of all these investigations of the external world should be to discover the rational order and the harmony that's been imposed on it by God. So in that context, then, I'm going to talk about 4 different generalized topics. I'll talk about ice cores and the kind of data that we can see from ice cores. And the ice cores reveal that we've been blessed with a uniform climate for the last 10,000 years as mankind has been here on Earth, and in the last couple thousand years now exploded to vary all over the Earth. Then I'll talk a bit about radiocarbon and how that process is done of getting radiocarbon ages, commenting about biblical archaeology as one application. Then to understand the behavior of the Earth itself, I'll have a segment on plate tectonics, which ties right into radiometric dating, and one of the ways that we can understand and calibrate our radiometric dating process. And then I've already mentioned the Grand Canyon book, so I'll make some comments about that. And I'm here significantly then to answer your questions as best I can. So first, digging into ice cores. This map shows Greenland, and there have been 4 to 5 significant cores that have been cut through the 2 miles thick of ice that makes that ice sheet up in Greenland. The data that I will be showing you in particular comes mostly from this one that's right there in the center, right at the crest or right at the summit of the high point of the ice where it's maximum thickness. There you can see that's 3,000 meters, so about 2 miles thick for that ice sheet. The Greenland ice cores for us here in the United States are stored in a U.S. Geological Survey repository in Denver, Colorado. And there was a professional meeting in Denver a couple of years ago, and I had the privilege of going into the laboratory and seeing the storage of them. This is the workroom where geologists can lay out the ice cores to work with them and study them. And then there's the entrance that goes into the ice room. And there I am with my down jacket in the ice room. And the temperature there is at minus 30 degrees Fahrenheit to keep completely frozen. Yep, I needed my jacket for sure. Although we weren't in there too long, but still, it's cold. The other room was just outside that one. That was kept below freezing, but not down at minus 30 for working. So in the Greenland ice cores, it's possible to physically see differences between the summer and winter behavior, what's happening. Of course, the snowfall is in the winter time. So the winter layer, more winter layers are lighter color because they don't have as much dust related to them. Whereas the summer layering does have hoarfrost that's developed with the sun warming up the surface and dust that falls down during the summer season. So here is a big long section of some of those cores that you can see the banding. And this particular segment, this photograph was from that ice core that's close to 7,000 feet deep. And the counting of those layers at that depth yielded an age back at 31,500 years, okay? So there's the location of the core and very much right on the crest of the ice sheet at the summit where it was collected. This data on the right-hand side, the squiggly line there, when the squiggly line is to the right, that means we have a warm climate. And when it is over here to the left, this is cold climate. So all this line to the left represents the last glacial period that we've had on the Earth that ended up melting away sometime between about 14,000 years ago and ultimately here at about 11,000 years, 10 or 11,000 years, coming to the current temperature that is really amazingly uniform compared to all the history in the previous 100,000 years. This red arrow represents where the ice came from in that picture that I showed you that was down at 31,500 feet. Now, the counting process is challenging in the sense that we know that some seasons there would not be necessarily able to identify a light and dark band. But what the geology community has been able to do is they take the ice and they melt the ice and they're able to collect little pieces of volcanic ash that has fallen on that snowpack over the time period that ice has been developing there. Those little pieces of volcanic material are referred to as tephra or tephras. And in this band between about 60,000 years and 110,000 years, geologists have been able to collect and identify 24 different tephras successively down through that long sequence. And here's an example of some of those. 14 of those have been recovered. That here I'm showing ages that come from radioactive decay and radioactive dating processes. They can tie the tephra that's collected in the ice to the volcano where the eruption took place.
Oh, wow.
And at the volcanoes, they have then enough igneous rock to be able to work with and get radiometric dating ages. So notice that this group of 14 tephras is giving us ages before the present from 28,500 years back to 40,000 years. So this is a checkpoint. There are calibration points that they can do to back up and support the physical counting of the annual layers that are in the ice.
That is so wild.
It's pretty amazing. And I was able to visit with one of the geologists that was physically on the ice sheet during the collection of many of these ice cores, several of these ice cores. And I asked him, how far back did you feel you could count that layering with the naked eye?
Right.
Because the ice sheet gradually squeezes down and the layers get thinner and thinner and thinner because of the load of ice on top.
Compression.
Yeah, it's compacted, it's compression because the ice sheet has flow out to the coastline down deep. And he said with their eyes, native eyes, they could do the counting about 50,000 years. So that's a piece of evidence that the Earth is at least 50,000 years old, that you can count layers of ice.
Right.
When it's deeper in the ice core, they use a tool that has, well, through all the ice core, they also lower a tool and they measure the resistivity with electrodes. And the resistivity helps to be an identifier between summer and winter time. So that helps to get the layering count when the observation is too finely laminated in two segments to be able to have confidence in counting it with your eye. So pretty neat set of data. And so this is the supporting kind of, those are, and the different tracks here, the blue, the red, and the green are different ice cores, and you can see how nice and tightly they overlap each other. There's the 28,575, and there's the 40,000. Okay, now I'm going to shift from Greenland to Antarctica in a particular ice core that's called the Vostok ice core. This was one that was drilled at a location down there called Vostok. The scale is completely different here. It's covering a much longer time window, because Antarctica is basically a desert in the sense of the amount of snowfall.
Right, yeah.
So the rate at which snow falls, the snowfall rate accumulates, is so much slower than it is in Greenland. So this particular record is from today at zero back 400,000 years. And it's the same kind of data in the sense that there is the squiggly line that represents, in this case, warm climate is to the top and the cold climate is to the bottom. And this was the window of time frame that I just showed you a few moments ago from Greenland. You can see how we go way back beyond the climate data that was in Greenland. So the geology here is that there have been cycles of glacial periods like this that are very long, separated by interglacial periods that are much shorter. So here is the most recent one, and going back in time, there's the second one, third one, fourth one, and that keeps on going in Antarctica, the oldest ice is about 1 million years. Several of the cores reach down to about 700,000 years, 800,000 years. And then not too long ago, they've been able to find one that they think reaches about 1 million years.
Oh, wow.
So what does it mean to say that there was a glacial period? Well, up there is Greenland, which still has an ice sheet, but during the ice ages of glacial periods, all of Canada virtually and much of and United States down to about the Great Lakes, covering the Great Lakes, and down to the coastline at New York. So the gravel that forms Long Island came from this ice sheet.
Right.
And that's basically what it looked like during the time window, say from 80,000 years ago till about 14 to 16,000 years ago. Ice sheet also was on northern Europe, in Scandinavia in particular.
Yeah.
So coming back now to the glacial maximum that are down here in the when this data is low, and the interglacial periods. There you can see the several of them, 4 of them. Notice that these peaks are fairly short, a short amount of time, whereas today we have had now about 10,000 years of very stable climate that we can see here in Antarctica, but it was expanded on the Greenland ice sheet, which I showed a few moments ago. Notice this, that at the end of an interglacial period, over these last 4 or 3 of these, the climate went back to cold fairly promptly, but that did not happen 10,000 years ago. We've had this stable climate. So this is basically a gift to mankind that gave technology, or gave mankind to expand and population growth that we've had now with a 10,000 years of warm, stable climate. Okay, what questions do you have about ice cores?
First of all, that's very, very cool that we can that we can map the volcanic eruptions up in Iceland with these particular layers. My first question before we get to everybody else, because I'm going to take the priority, is
you got the mic. Go for
it. Can you map the Vostok cores up that small period of time that you kind of showed a bracketing and you were like, this is what we just covered up on Iceland? Can you put 2 on top of each other and get the same kind of temperature swings?
The temperature cycles will be comparable. They're very similar.
Right. Yeah. I would imagine they'd be slightly different because they're complete opposite ends of the planet.
Yeah, they are, but they show the same general pattern.
Oh, that's awesome. That's so cool. Well, so I guess, okay, so my first inkling too would be, what would you say to a perhaps someone who is proposing that ice cores are simply a result of very quickly depositing snow, fast blizzards, if you will? Would there be a way to feasibly argue that?
Well, that's the argument that is sometimes made, that all this layering is actually
rapid.
Multiple storms in a single year. But if that were the case, we wouldn't have those tephras that give radiometric ages that go back to 20,000, 40,000, 60,000 years ago.
Right.
So even though there is uncertainty, some seasons there wouldn't have been snowfall, other seasons there might have been multiple layers. So the uncertainty, the error bars on the original counting of the process, the error bars were fairly large. There was uncertainty. Different teams did the counting process, and the lines didn't fall on top of each other very well. But it wasn't the case that those 60 to 80,000 years of bandedness are not crammed into, just a couple thousand years. It's clearly long, even with the error bars. But then the radiometric dating helps to pin it down and saying, yes, this does represent passage of long periods of time in the tens of thousands of years.
Right. Oh, that's beautiful. That's awesome. All right, let me see what we've got. We have some general questions.
I'm listening.
Yeah, so Scott Duke wants to know what you, in a slightly off topic, they apologize for being off topic. They asked you what your thoughts are about the volcanism currently going on in Iceland.
Well, the volcanism in Iceland is part of plate tectonics, in that at all the plate boundaries, and Iceland is right on the mid-Atlantic ridge. So there are hypothermal vents there. Those rocks, are forming continuously. So that is an area where there is continuous, stronger and not so strong volcanism, just like the islands of Hawaii that we'll talk about a little bit later.
Right. So a side note question with regard to comparing ice cores from Antarctica versus the ones that we find up in Iceland.
Yeah.
And maybe it was a lapse in my understanding. What is the reason why we can go back so much further in Antarctica rather than Iceland only going back a couple 100,000 years?
Yeah, and just a mild correction, that's Greenland, not Iceland. Okay.
Oh, my mistake. I'm sorry, Greenland.
That's okay. The ice sheet is on the Greenland little small continent. The difference is snowfall on Greenland is high. So it only covers about 100,000 years. In Antarctica, snowfall is very, very low.
I see. Okay, right.
So that's the key to the difference.
Right. Our friend, Mr. Wilford, for a super chat for $5, wants to ask you what your opinion is on the Lost Squadron argument.
Yes, I'm glad to talk about that. Thank you for raising it. In case you don't know if somebody doesn't know about the Lost Squadron, in World War II, there was a time period where a crew of about 5 or 6 planes were flying over to Europe, and they realized with their visibility conditions hampered because of clouds, they were not going to be able to make it the whole way over to England. So they ended up coming on back, and they had enough fuel to be able to land on the ice, on the Greenland ice sheet. Well, that landing was about, it was back at the end of World War II. So let's say 1940, I'll say 43, 44, 45, something like that. Okay?
Right.
The planes landed down along the coastline, very close to the coastline.
Right.
And over the 50 years, they ended up being buried in about, my memory is telling me something like 250 feet of ice, of snow and ice. One of those planes was found after teams went up there for 2-3 years, and they finally were able to find them. It was pretty challenging because the ice sheet had moved them somewhat toward the coastline, and then they buried them. They were buried fairly deep. Well, they eventually did that. They were able to recover them. So a young Earth argument says, oh, that snowfall is so fast that there cannot possibly be 100,000 years of ice up on the summit.
Right.
But the key to the difference is the snowfall down along the coast, which is influenced by the Atlantic Ocean. Snowfall is very high, whereas up on the summit, snowfall rates are very low. And we do the counting, and we get the confirmation with radiometric dating of those volcanic ash tephras that are there. So that's an argument that's made that is pretty common in young Earth creationism literature, but it lacks validity because it's yes, they were buried under that amount of ice, but there's a reason. It's because snowfall is very high along the coastline.
Right. I think that raises an excellent point that I personally try to bring up whenever I can when we're having the discussion about the age of the Earth, which is this method of corroboration, this massive cross-corroboratory methodology that we have within geology, but indeed also fingering outward into other fields like dendrochronology, or how coral clocks grow, or how coral reefs grow, and you can clock their growth and match that along with radiometric dates as well. And I think that corroboration, one, and that you of all people would attest to this, it's that we use that in our industry in order to find the reliability of radiometric dating, to find oil and other fossil fuels. That was a superb answer. I hadn't even considered that, but that's awesome. Would you like to move on a little bit and then do another series of questions here after we're done with the next section?
That's fine. Okay.
Awesome.
So we'll talk about radiocarbon. Carbon-14 is produced in the upper atmosphere because cosmic radiation and solar radiation bombard the Earth and causes carbon-14 to be produced from nitrogen. It gets taken up by the carbon dioxide in the atmosphere. Carbon dioxide is taken up by the plants and leaves. So the carbon-14 gets into the tree rings of the trees, and animals that are eating the grass. The carbon-14 gets into their bones. So that's the source of the carbon-14 that gets down onto the surface of the Earth and gets taken up in tree rings and bones and coal and things like, and organic materials. Okay.
Right.
So as trees grow, if there's a wet season, the tree rings will be fairly wide, as this example shows.
Mm.
When there's a dry season, the tree rings will be fairly narrow. So with wet and dry seasons, there's a pattern behavior here of narrow bands and wide bands that we'll look at. And here's the context. This is a living tree over here on the right-hand side, and there's a segment of the tree that shows the banding. And with the wide and narrow bands, sort of like a barcode in a grocery store, here is the bandedness from a tree that is recovered, as you'll see in a moment, from a log cabin. And so the confirmation of that these particular tree rings grew in the same year as these, in the same year, ended up that we have an overlapping period of time here, such that the wide bands in both will have the same amount of radiocarbon, and the narrow bands in both of these will have the same amount of radiocarbon. So
that's awesome.
Count back in time, and we can extend that beyond the living trees and this kind of a pattern. So there is the living tree. So we can start counting here. Going back in time, there's a log from a cabin. Here's a log that's lying on the ground out at the surface, and here's a log that's been buried down in the rivers, in the river mud. This step is called cross-dating of the tree rings to get a count that goes back much longer than any individual living tree.
Right.
Now, the radiocarbon that gets taken up into those tree rings undergoes radioactive decay, and the mathematical description of the radioactive decay is referred to as half-life, which is the time that it takes for 1/2 of the parent atoms of a radioactive type to decay away to daughter atoms. So on the left here, this block has 64 purple atoms being all radioactive in carbon-14. After the passage of one half-life, there are 32. After a second half-life, there are 16. After a third half-life, there are 8. And after a fourth half-life, there are 4. So that is the pattern that shows up on the radioactive decay process of all radioactive type atoms. Another way to think about it is, here I have an example, say, of carbon-12, which is stable, with 100 trillion atoms of carbon-12. Today, carbon would get into the tree rings at about, say, 100 carbon-14 atoms. So once that tree ring has formed, then after the passage of one half-life, which is 5,730 years for radiocarbon, there will be 50 radiocarbon atoms left. And after the passage of a second half-life to 11,460 years, there will be 25 atoms left. So that's the context of thinking of radioactive decay with respect to half-life.
Right.
Now, this is an idealized kind of graph that represents percentage of carbon-14 remaining. 100% we refer to as the amount that gets into the tree rings today as the trees are growing. And then with the passage of time, it follows this very regular pattern of decay away with half-life back to about 50,000 years, when there's less than 1% of the original still there. Now, suppose we find a bone from a mastodon, and if we have 6% of that radiocarbon left, we can come over to this reference line and recognize there's that amount of radiocarbon, and that represents the passage of about 23,000 years. So that's the concept of being able to select and calculate a time when this mastodon lived. So we're going to combine two methods now here, treat these two together. So the carbon-14 content is chemistry or geochemistry. Tree ring growth is from biology. We're going to look at these two together now. Those that are persuaded the Earth is young raise these challenges. That is, that trees could grow multiple rings per year. And they make the claim that geochemists assume that the carbon-14 production in the atmosphere remains constant over time.
Right.
Well, we have to test that. We have to verify that we don't, that this whole sequence is not just multiple rings per year, because there are some tree species that do grow two rings a year. That does happen sometimes. And on the second claim here, we just don't assume that production is constant. That's just a faulty description, because the individuals claiming that do not understand how we do the work.
Right.
Okay. Now, knowing that we have a certain amount of production of the carbon-14 in the atmosphere today, we can draw the decay of that back through time, in this case going back to about 13,000 years. We know that there is variability in the production of carbon-14 in the atmosphere, and we have some estimates that we can get from other isotopes that are also produced in the upper atmosphere by cosmic ray bombardment. So an expected range of the radiocarbon falls between these two blue lines that we have on this graph. So if, in fact, lots of trees were growing many rings per year, the data would end up falling above those lines of expectation. If there was much less carbon-14 in the atmosphere, or if the decay rate went so much faster than we think it does, the data would fall below the lines. Another big advantage of doing the radiocarbon is that we might have done a mismatch, the rings of those barcodes of wide and narrow bands. We might have accidentally not matched them correctly together. Well, the carbon-14 in there can confirm that and help us ascertain that, yes, we've done the matching properly from a living tree to dead trees into the past. And we can make that as a correction to get our results coordinated between these expected range.
A way to check your work.
It's a cross check. It's a physical test. We have to test and verify each step of the process, and that's part of that process. Well, look where the actual data comes from, and this is data from German oak species in Europe that have had their record collected. Teams in Europe and Dendrochronology experts in Europe have dug thousands of tree trunks out of the rivers across Europe, the Rhine, the Rhone, the Seine River, etc. And they've done the counting of the tree rings, and they've measured the amount of radiocarbon, and it falls just like expectations. And this is then showing the nature of the variability. You can see it's a squiggly line.
Right, right.
That very specifically reflects the fact that there are variations of the production from solar radiation is variable dependent on the sun. Now let's make an application then. One example here, biblical archaeology. The Dead Sea Scrolls were found in 1948, 47, and they were found in a cave in Israel. And the claim about this particular Isaiah scroll, it has a very precise description of the crucifixion that happened when Jesus was then crucified in Jerusalem in about 33 AD. Critics of the Bible claimed that this must have been written after those events, or nobody could write it that way. Well, these Dead Sea Scrolls being found here in the 1940s have had a radiocarbon date done to them. And this is the range now from today back 4,000 years. And and here again, you can see a very good example of the squiggly line of the variations of the solar production. The Dead Sea Scrolls ended up with about 76% of the modern carbon, and that takes them back to about 2,100 years prior to today, or in other words, it puts it back in BC or BCE as many people refer to it now, before the Common Era.
Right.
So there is just a piece of evidence that supports the fact that those scrolls were almost certainly written prior to the prior to the crucifixion. Okay, there's an example then of that's the data that I showed. Now looking on back beyond that, back to 50,000 years. Oh, here's another example of of tree ring data. My college where I got my chemistry degree is in Wheaton, Illinois, and in the 1950s there was some excavation done on a property owned by the Perry family. And thankfully, somebody running a bulldozer began to see some things that might have some archaeological interest. And they ended up finding the bones of a mastodon. Well, the Perry family was very gracious, and they gave the bones to Wheaton College. So in our science building there at Wheaton, where I did my degree, we have that reconstruction there of the Perry Mastodon, and this is in the right in the lobby of our science building.
That's a beautiful recreation.
It's amazing. My colleague Steve Moser took some of the bone and he had it sent for radiocarbon dating, and in that case, it had about 26% modern carbon. And that came out to a calibration of about 13,500 years, plus or minus 60 years. So there's a time window now and an error bar that goes along with it. Tree rings application, the current limit is about 14,000 years. Even though trees lived before that, geologists haven't been able to get a continuous record of cross-dating.
Right.
That they could have confidence that it was tied together continuously. Now, the other line that I showed you is physically a reference line to show the idea. This slide is an example of the actual calibration curve that comes from those samples that take us back to 14,000 years. There's the last data points in the calibration curve at about 13,950 years, okay? So the tree rings that are measured in the laboratory with an amount of radiocarbon are then plotted versus the count rate, the physical counting. So in other words, you can use radiocarbon if you can count tree rings. So the horizontal axis is calendar year, and then the vertical axis is the physical measurement of the quantity of radiocarbon. And here's another example that you can see the nature of the variations that are influenced by the solar radiation from the sun. So content is this amount of radiocarbon is in it, and that then comes into the calendar year of 13,500. Okay.
That is just that's the precise shape that you want to see when you're inputting, trying to see if it's going to match your hypothesis, right? You've just got that really smooth, linear, just beautiful graph right there. I love it. That is so cool.
Yep. Okay. There's the 14,000 years for tree rings. Now we're going to combine 3 different methods, okay? Here's the radiocarbon chemistry. Here's the tree rings of biology. And now for beyond 14,000 years, we're going to do geology, sedimentary varves. All right. There's a lake in Japan that is called Seogetsu Lake, and it's nicknamed the Miracle Lake because the combination of factors there are so dramatic to give us these sedimentary varves that we are able to confirm that they are actual annual varve layers deposited individually year by year. Here's the river that brings storm-laden sediments, say down here, and it first enters into Lake Makata. So this Lake Makata is sort of like a sand trap that traps most of the sand and coarse material from a storm. And there's a passageway there into Lake Seogetsu. So it's only the fine material that gets through that passage. Most of the coarser sediment is over here in Lake Makata. So Seogetsu is just an idealized kind of setting, and it has differences of deposition in the summer or the winter time. So there's some clay in the autumn or the winter. There's a mineral siderite that's in the autumn. In the summertime, there's a light amorphous organic matter that is the layering. And these are some of the diatoms that live in the water in the spring. And then those diatoms fall to the bottom and help to make that layer. And there's an example then of some of the sedimentary material. That's the white summer layering and the dark of the winter time. So these sedimentary varves are also counted in several different ways, both eyeball and with chemistry.
Right.
Now, this is my colleague, Greg Davidson, with whom we've written papers together that are written for the church community. And we were at a meeting of the American Geophysical Union, and I called Greg because I learned that this gentleman from Japan that worked on Seogetsu Lake was there at the meeting. So I called my friend Greg and he said, I'm busy, I'm in a meeting. I said, Takahashi is here from Seogetsu Lake. And he said, I'll be right there in a minute. So we had no idea that he was there. We'd read about these materials. We'd read some of his technology that they did to handle those cores, and here he was. We had a chance to see him in person. It was really pretty.
The ultimate getting to geek out with someone who wrote one of your favorite papers moment is just. Yeah. It's a very, very niche feeling, but once you getting to meet someone who wrote an excellent paper is just as humbling as it is cool.
Yeah. Okay. Now, Geogetsu data. Let's see where that falls. Again, these are the layer. The blue lines are what are the expectations if the radioactive half-life is in fact 5,730 years, and if there haven't been excess, lots of extra varves, they would not fall together. And voila, look at that. The data falls very nicely within those expectations. So we have a strong support here that we have 3 different, basically scientific technologies that get built into one particular story for this data of radiocarbon. We're going to look now at an overlap, because from 10,000 annual layers to 14,000 annual layers, we have data with both the tree rings that are coming down here and all the red points, okay?
Right.
And in Lake Geogetsu, we also have the data that comes from the varves, and just notice how well they fall on top of each other. And right in this position, we have at tree ring number 11,240, we have a correlation point that is very good, that gives us the opportunity to tie the varve count to the tree ring count. So back to 11,240 years, we use this data to carry the radiocarbon analyses on beyond the 14,000 years. So we tie the two together at that point.
So the thing about that's just so amazing is that, in nature is different from math and physics in that you tend to not get beautiful, perfectly straight lines.
Bingo!
So this is about as good as you can get as far as something that is perfectly linear. That is such a great way of visualizing just how these fields manage to map on top of each other. And I would wager that you could do the same thing with other aspects of geology, dendrochronology, and biology as well. That's so cool. I had not thought to do that with those 3 in particular. That's a great visualization.
Yeah, it's an incredible story. And we have all this written into a paper. I don't think I've sent it to you yet, but I'll send it to you now.
Yeah, that would be great. So I can put it in the description and everyone can kind of check it out for themselves. Yeah. Origami Swami says, wow, even earth rings. They also say, the same individual, what would you say to encounter someone who would perhaps you're using the tree rings to calibrate the carbon dating, but you're also using carbon dating to confirm the tree rings. It's circular.
Yeah, that is a common statement, and that's something that the individuals that are saying that do not understand what we're doing.
Right.
Okay. This data point, this vertical scale, is a convention that is used by radiocarbon community to represent the quantity of carbon-14 measured in the tree rings. Okay? So that is raw physical data.
Right.
The notation we put into and refer it to as radiocarbon years.
Right.
But it's just the physical measurement. So then when we have an unknown sample of an unknown age, and the data there comes the physical number of years where those tree rings lived is on the horizontal axis in calendar years. Those are the ones that are counted.
Right.
Then we have that as a calibration curve that we can come into this data with a sample of unknown age, unknown calendar years, come over to the calibration line and come back and get calendar years before present.
It's the logic behind it, as far as I can tell, is very similar to just any kind of mathematical formula.
Exactly.
If you have two of the variables, you can find the third. That's just the nature of how these variables are dependent on one another. Mr. Wilford, for $5 as a super chat, wanted to ask you, or I guess just double check with you, aren't there ash layers at Sugetsu which line up with varve counts as well?
We do have, yes, we have those, and we have that in one of our papers. Yeah, we have that in the paper. There's a volcano from nearby there in Japan that has an ash layer that was dated, okay.
Yeah, yeah.
And confirmed. And we have that in the paper. I just don't have it in this talk.
Yeah, that's awesome. Add another corroboratory measure.
Exactly. Yeah, exactly. That's the whole.
That's awesome. Okay, I think, let me double check. Let me make sure. Double check here that we don't have any more questions on this particular section. No, mostly everybody's just geeking out about how cool it is. You're explaining it too well, Ken. You've got to be a little vaguer so that people have more questions.
No, I want them to understand the best that I possibly can. That was the advantage that I've had basically 15 years of teaching non-geologists in the oil companies about how we find oil. And so I learned not to use rather rare geology terms. I try to put it in terms of that are understandable to anybody as best I possibly can.
I as a side note, as a fun side note, I wanted to say this earlier, but my future brother-in-law is out in West Texas right now drilling in a Permian basin. It's just when he told me that, I was like, I know the Permian.
Yeah, it's a major producing basin. It's produces the most oil of any of the basins in the U.S. right now. Yeah.
He works for Pike out there, so they're doing a lot of drilling.
Okay.
All right. Let's keep.
Let's step to plate tectonics and the ideas of radiometric dating. Here I'm referring to radiometric dating of atoms that have a long half-life, much longer than radiocarbon. The Earth is made up of a series of about a dozen plates, and you can see the characteristics of the arrows and that the plates are spreading apart. And right at the beginning, we were talking about Iceland. You see how Iceland is right on the mid-Atlantic ridge. So there's volcanism there on a regular basis. The mechanism that drives it is because if you look at this beaker, say that be a Bunsen being heated up in a laboratory, if it's heated by the burner right in the center, the water is hot, gets hot, and it rises and it has to sink along the sides because it's constrained within the beaker. The outer core is molten of the Earth's core, and it provides heat that heats up the mantle. And the process is the mantle rock is sort of like Play-Doh. It's not solid rock. It's not solid rock, but it flows very slowly.
Right.
So there are convection cells in the mantle characterized by the way these arrows show. And that ends up carrying the oceanic crustal plates apart from each other. So the mid-Atlantic ridge is where fresh mantle rock comes up right in the middle. And as it adds new oceanic crust, so that the Atlantic Ocean is slowly getting wider and wider and wider.
Some seafloor spread, yes?
It's exactly, seafloor spreading. So we're going to look now at the Hawaiian island chain and emperor seamounts that go on up to the Aleutian Islands. This is an example of the way the plate is moving to the northwest, so that as the plates move, they cause earthquakes to occur at the boundaries where the rocks break apart. There are the volcanic eruptions that occur, as you mentioned in Iceland here recently. When the Japan broke loose, it caused a serious tsunami that damaged that nuclear power plant, ends up building mountain chains and islands. And here, example, there's the tsunami that hit Japan in about 10 years ago. And the big island of Hawaii, Kilauea volcano, has particularly active about 2-3 years ago. And what is happening down there is the islands of Hawaii have been constructed basically by lava coming up through the oceanic crust. And all the publicity that we had a couple of years ago, forgetting the year, was it 2018, I believe? Lava was flowing down through the neighborhoods and through forests and covering roads, damaging property, et cetera, in the process. This is nature in action. So here's the context. As the plate is moving to the northwest, a hotspot in the mantle down here is providing lava that comes up through this plume, and it first builds up on the seafloor. Then when eventually enough lava has come up and cooled, it produces the islands that are up above sea level. And in fact, even today, to the south of Hawaii, just offshore somewhat, the next island is under construction underwater. It's still underwater at this point, but it'll eventually come out to the surface. So the successive islands to the northwest have been built like this over the last 80 million years, as we'll see in a moment. There's the big island of Hawaii, and some of the older rocks on the big island are 400,000 years. Then successively, the islands to the northwest, 1.3 million years, 1.9, 2.6 is where Honolulu is. And then the island to the northwest is 5 million years. Now, the concept is that these ages that I'm putting on this come from potassium-argon radiometric dating, where the rocks were collected from the islands on the surface or with the submarine mountains, sea mounts, an oceanographic vessel with a dredged up some of the igneous rocks to get them to the laboratory. So there you can see 0 for the big island, and then those up to 5 million years, which I showed in the previous slide.
Right.
Then successively, the numbers keep on going past Midway Island, up here to this bend at 43 million years, and then finally up there close to the Aleutians at 80 million years, okay? If radiometric dating did not work, and if it were bogus or some reason, you wouldn't see this very regular trend.
Oh yeah, it's stepwise. It's
stepwise. Yeah, it's just basically geology doesn't get better than this sequence, I'll tell you. It's really incredible. So we have a distance of 2,200 miles from there, the big island of Hawaii to the bend at 43 million years. So we can calculate a rate at which it moved, 3.2 inches per year on average. Up here we have 1,500 miles, and we have an average of that movement of 2.6 inches per year. So you see the physical movement of the plate that we can identify because of the radiometric dating has extended our understanding of how long this process has been happening to form that portion of the islands of the and the seamounts over that hotspot in the mantle. Well, how can we trust radiometric dating? we can compare it with the other data recorders, which we're doing right here in this example of the data recorder is the plate moving. It's incredible.
That stuff blows. I know you're about to get into it because I just wanted to point this out, that when I think of Grand Canyon Monument to an Ancient Earth, this is one of my favorite things that I did, which is how the movement of the tectonic plates corroborates radiometric dating. So I'm so excited that you're getting into this.
Okay, now, so we have the data. Now let's see if it still works today. We have satellite technology today that it's possible to measure positions on the Earth's crust very precisely, and if they are moving, physically moving. Well, this map of the world has black arrows that shows, and the length of the arrow represents the amount of movement that, for example, Hilo, Hawaii on the Big Island is moving today at such and such a rate of inches per year. And that is physically measured with satellites. And you can see all of the other arrows that are moving in some cases in different directions, but that's the result of being able to do this measurement with satellites. Well, how much is it moving today? 3.1 inches a year. Voila, right between the 2.6 and the 3.6 that we measure from radiometric dating. So here is an historical tool of radiometric dating over the last 80 million years. And now in the last 10 years, the physical measurement of this position of Hawaii, we confirm that yes, that is a reasonable rate of movement over the whole period of time. It doesn't get any better than that.
You really and truly couldn't ask for a better representation.
Yeah. This is that's why we as geologists and I as a Christian geologist can have good confidence that these are credible results. I'll do a little bit more about the clocks in the rock, but I'm up to about an hour. So let's just do a few here and then break off and let people ask questions. Here's another representation of the radiometric dating with its exponential decay. This is the same theme of 100 blue dots. And as passage of time, all radioactive atoms undergo this decay of characteristic half-life. Here you can see that out at about 7 to 8 to 9 half-lives, that there's less than here's about 1% of the original is still left behind at about 7 half-lives. Igneous rocks are a critical step because the timer is set when the molten liquid crystallizes to a solid. That sets the timer T=0 to start the counting process.
Right.
An example here, uranium-238 atoms undergo a multiple series of steps, but end up as a daughter product eventually of lead-206. So the atoms of uranium are trapped in different minerals here in the rock. And I'm going to show a schematic of how we can use these tools to get the age of rocks. In this case, the uranium-238 half-life is 4.5 billion years. Now I'm doing a schematic here just to give an impression of how this could work. Zircon minerals in particular are a mineral that take up uranium. So I'm showing a picture of the mineral with, a dozen uranium atoms there on the surface.
Right.
Thinking of that as 400 million years ago when it first started. So it's only uranium in there. A different kind of mineral ends up picking up the potassium atoms, including potassium-40, which is radioactive. Those are in feldspars. It undergoes radioactive decay to argon-40. Uranium-238 has a long half-life, so it decays away at a slow rate, whereas potassium argon decays away at a faster rate So I'm showing 2 atoms of potassium-40 left here and about 6 or 8 atoms of uranium still left over there. So these are 2 different half-lives. We can go out in the field today, measure the quantity of the parent and the daughter products, and determine and get an estimate of when, a quantitative estimate of when that mineral formed as a solid. We use about a dozen different radioactive atoms, and this is just a group of about 5 of them. There's the uranium-238 that I've mentioned. There's the potassium one, and there's the uranium-235, and then there's radiocarbon that can be used for organic materials. So the geologic time scale that was developed looking at fossils in the 19th century established these various different periods of the Cambrian up through the Quaternary with a fossil sequence. When radioactive decay process was discovered in about 1898, then over the next 20 to 30 years up into the 1930s and 40s, geologists developed the tools to do this radiometric dating that I've just mentioned.
Right.
So we have been able now to add an absolute time scale to these by doing radiometric dating of volcanic ash in volcanic rocks that are scattered through the whole sedimentary sequence. The history of the geologic time scale, those were basically identified in the 19th century, and they're the years that the different names were identified.
Right.
And then how can I trust this radiometric dating? Well, I showed that one example with plates moving. I'm going to show one more here yet, testing it against a volcanic eruption of known age. Mount Vesuvius erupted in 79 AD and destroyed Pompeii. It was so catastrophic that the people who were in their houses could not escape. And so archaeologists have prepared these as examples to sort of review the history of that explosion and how and the people that got caught in their houses. There it is today, Mount Vesuvius. The atom used for radiometric dating on this was potassium-40. It undergoes a radioactive decay to argon-40, half-life of 1.25 billion years. So from 79 AD to the year in which they sampled it, I think this worked out to 1977, was 1,918 years. Geochemists applied a method that's referred to as the argon-argon age, which is a specialized and improved version of just plain potassium argon. Right. And notice that the result is 1,925 years plus or minus 94 years, which is incredibly right within. So here's a case where we've tested the argon-argon radiometric dating process against this known eruption about 2,000 years ago.
I've read that. I think that's a 1998 paper, which is just such a cool paper.
Is that a coincidence? Nope. It's the result of good, careful analysis for things that work. And I think for my timing a little bit over, well, let's see, age of the Earth, let me do the age of the Earth yet.
Oh, yeah, please.
Yeah. For the age of the Earth, we're looking at uranium again that goes to lead with a half-life of 4.5 billion years. Geochemists derived a very ingenious method for estimating the age of the Earth. They have identified the fact that this is Meteor Crater in Arizona, and they have some of the physical meteorite that they have uncovered there. And that meteorite material has no uranium in it. So it is entirely made up. So there's no uranium. So during the history of that particular rock from when it was molten, the lead isotopes have remained the same because there's no uranium there. The two individuals two of the authors of that original paper in the 1950s, one is Claire Patterson, and he was at Caltech, and he's a specialist in particular in lead isotopes. The other person that was involved in writing that first paper is George Tilton, and I had my very first geochemistry class with George Tilton because I was at University of California, Santa Barbara 1 year before I went to Columbia, and he has had a whole career, distinguished career in this geochemistry, and he had a worldwide reputation similar to Claire Patterson. And their idea was the following. In the Earth, the uranium is going to be steadily decreasing since the Earth first formed, and lead continued to increase. So they wrote the equations to determine how long did it take the radioactive decay of uranium to change the lead-206 composition in those meteorites to that was in the Earth's crust. And the result was 4.56 billion years, published in 1955, 1956. So we have had that now for over half a century, and that age of the Earth has hardly been changed since that time. Here are examples of meteorites that have similar ages, in this case with 4 different methods with 4 different half-lives: uranium, lead, rubidium, strontium, potassium, argon, and rhenium, osmium. 4.55 to 4.5 to 4.62. Radiometric dating does work.
I think that might be safe to say.
We just have amazing tools to test and verify our understanding of Earth history. That's what I enjoyed, knowing God as my creator and then seeing these things that He's done. It's been a real privilege to study geology and geochemistry in the ways that I've had. Well, I think we ought to pass on the Grand Canyon because that's our time. We'll do the Grand Canyon another time.
Yeah, maybe I'll might try to come back on, and I do love talking about the Grand Canyon. It is just specifically a very cool structure, and a unique one. It's we don't find those every day.
Yeah.
I wanted to comment too on the dating of the age of the Earth, being around 4.5 billion years, 4.56 billion years. Just a couple of days ago, I believe it might have been last week, might have been a week ago, there was another massive impact crater that was discovered in the Sahara that they dated. More came to that same conclusion. So, I mean, this is a August 2020 paper, but I'd only stumbled across it last week, I suppose. So, that still continues to hold up, which is, I don't think, like you said, I don't think that that's a coincidence.
When I send you papers, I'll also send you one by the geochemist who actually did that potassium argon dating.
Oh.
And he's written books on the ages of the Earth and the solar system.
Right. Well,
rocks, meteorites, and the moon, etc.
We have some awesome questions. They go back a little bit, so we'll kind of just start at the beginning.
That's fine.
Yeah, Origami Swami wanted to ask you, what caused the change in the direction of the bend in the Hawaiian Islands expansion outward from the Mid-Atlantic Ridge?
Well, okay. No, you said the change of the bend in the Pacific Ocean basin, okay? So that's just a big plate moving.
I'm sorry, my mistake. My mistake. Yes.
Yeah, yeah. That had to do with things that were happening in the mantle.
Okay.
And the way the plates were moving around, affecting and the mantle movement. So there was a physical change. I haven't read. Well, it's been some time since I've read sort of what the issues were that caused the shift. It had to do with the nature of some of the other collisions that happened about that time window.
Yeah,
it's so obvious, so you can't miss it. It was about 46 million years ago. It's just, it's just bold right there.
Yeah, you've got it. That it's got this nice little J shape almost going on there. Yeah. Very cool.
Yeah.
Yeah. Here, let me add that back up so that everyone can see it. Yeah. So if that's the one. An L, I guess, would be. Yeah, an L would be a better way of putting it. Yeah, that's really cool. I was thinking the same thing. I mean, again, geology, not something that I tend to know super well, but I'm imagining that, anytime that you get these drastic changes in plate direction, it almost has to be because a plate somewhere else is crashing up against something new, so to speak. They also wanted to ask you, they say, I'm not clear on why the rock solidifying marks T = 0 for the decay clock. So for the slide that you had T = 0, yes. They say surely radioactive elements decay in molten rock as well, right?
That is true. Okay. The radioactive atoms are decaying all the time with their half-life, period. Okay? But if the lava is molten, the decay product gets separated from the crystal, from the uranium, from the parents and the daughters. They get all mixed up. The significance about the cooling and chilling down is that once the uranium or the potassium is locked in a crystal, then when it undergoes decay, the lead stays there, like in that little bird's cage in the crystal lattice.
Right.
Because we have to get a measure of the parent and the daughter. If we just had still liquid, we don't have any way to get an age of that particular rock because the rock hasn't formed yet. There is no rock yet.
Right. Yeah. It's the trapping that allows formation, right?
The physical trapping. So when we say the age of a rock, of an igneous rock, it means when it formed from a liquid to a solid.
Okay, right. And it starts the timer.
That starts the timer, yeah.
Yeah. Okay, cool.
Yeah.
Scott Duke asks, they say, I saw a young Earth creationist argue that there's too much helium present in zircons for the dates to be correct. Has Dr. W heard that argument, and what would be his response?
Yeah. The way it's often presented is that the helium, because there's helium still there, the Earth must be young.
Yep.
The speakers do not tell their audience that there is still uranium in those zircons and it's producing it all the time.
Mm-hmm.
And that uranium will produce the helium for the next 4.5 billion years also. The radiometric dating method, as I showed you here, is uranium to lead.
Right.
In the 1910s and 20s, as geochemists were first thinking about using radioactive decay to get the age of a rock, they knew that uranium decayed to helium. But they found that helium was an escape artist. It didn't stay in the lattice. It leaks. Okay, it leaks out. So the radiometric dating method is uranium to lead.
Yep.
The idea of uranium helium was abandoned by geochemists 100 years ago. It's not a dating method.
Right. Yeah. So there being the question why it's being asserted by folks now.
Because somebody who's a genius found a way to make a curve of the diffusion and make it look as though that happened about 6,000 over the last 6,000 years.
Yeah, there's a very similar argument from the from that kind of gang about cold slabs, and how we're finding cold slabs, subducted cold slabs. They're too cold to have been subducted if we've got this ancient time scale. And the branding is key there, because what they don't tell you is that they're not cold like you could touch them cold. They're just colder than the surrounding mantle. They're still incredibly hot. There's not something off my shelf. They're still incredibly hot. So, the branding is I imagine it's something quite similar as far as how the idea is being disseminated, right? It's all about the wording.
That is true. Yeah.
We've got Jonathan Baker is in the side chat. Hello, Jonathan.
I just reread those papers. In fact, I just heard one of those speakers with the cold slab just within the last 2 weeks. So.
Yep. Yeah, it's interesting how they kind of cycle through. Okay, let's see. What else do we have here? Okay, Big Brother has
maybe what I should say a little bit more about that helium. Physically in the laboratory, there were some measurements made of the diffusion rate of helium out of the zircons. So there was some laboratory work done, so that diffusion step was a physical measurement.
Right.
Now,
yes.
I don't have the right math background to investigate diffusion processes, because they're far more complex than half-life. I understand radioactive decay with a decay equation, with a exponential decay equation, but by comparison, diffusion is incredibly complex by comparison, and it's highly dependent on variations in temperature. Nobody can know the nature of the history. So how he came up with there is a gentleman that I know of who's written some papers about that diffusion process, and that work that's been done and reported by Younguth is done at the incorrect. It's either incorrect pressure range or temperature range. He was in the incorrect range completely, and as he did the work, and he came up with his 6,000 years.
Yeah, I feel, and my memory on this is a bit distant as well, but I feel that I remember reading specifically with the helium that one of the primary sites that's utilized by young Earth creationists is the Fenton Hills, which is known for being very thermally catastrophic in nature. It's just constantly swapping around. So it was just, if this is indeed a robust case, why would you not go to a much more what's the word I'm looking for? Geologically consistent area to sample from.
The radiometric dating method of Fenton Hill is uranium to lead. Right.
Oh, okay. Big Brother has a question for you. They say, do you have an estimate for how much of the Earth's crust has been stratigraphically mapped? I think I know how much we know.
I'm not sure what you mean by how much of the Earth's crust. There have been geologists all over the world on all the continents. So there's geology work done on every continent.
Right.
The oil industry has drilled into every sedimentary basin. So I'm not quite sure what the question is.
I think it's more akin to, typically a lot of times you hear folks say, we know much more about the surface of the moon than we know about the bottom of the ocean, mostly just referring to, would it be possible for us to run into geologic unknowns, I suppose, if we were to go to a new location that hadn't been mapped?
Well, the seabed is mapped very, very well. with
like sonar.
Yeah, like sonar.
Right.
Yeah.
I'm not scared of it though.
Yeah.
The deep ocean wigs me out a little.
Yeah, and man has been down to the deepest parts of the ocean in the Marianas Trench.
Yeah, the Challenger depth.
Right.
The Challenger.
And and various locations in the deep sea have been visited with submersibles.
Yeah. So, okay, so I would love to pick your brain about a question that I have very briefly
Go ahead.
While we're waiting on more questions to come in. And just remember to tag me if you have a question for Ken. With regard to your work in the oil industry,
yeah,
I believe I asked you this on the phone as well, but I would love to kind of dig into it a little bit more.
Go ahead.
How often in the oil industry is it important to understand the age of the Earth and radiometric dating?
Well, working in a basin, it's not critical to give a process, but we identify the sedimentary rocks with the geologic timescale. So that's just an automatic part of the process. Right. In that if the fossils have identified a certain sedimentary section is such and such a geologic age because of the changes of the the evolutionary sequence of the species that are there in a particular set of sediments. We just automatically are using the reference of time. It is not integrally critical to, use the absolute ages per se, but it's just part of doing geology. It's
right.
automatic.
Yeah. I'd asked my oil driller future brother-in-law the same question because I was just curious because when he mentioned that they were doing Permian drilling, I thought, what a perfect opportunity. I was like, so you guys know it's Permian? And he was like, well, the average folks that are out there drilling know that it's Permian. That's pretty much like the limit as far as the geology is concerned for us because we're just out there drilling. He said, but that being said, it's really important for the companies to not waste money drilling in spots that aren't going to have that aren't going to produce any oil, any fossil fuels. So oftentimes that's the whole gig with having geologists out there, folks who know what they're doing, because they can go out and survey an area and say, well, based off of either radiometric dating or the fauna that's found there, or fauna that is found fossilized there, we can say that this area maybe is or isn't good for prospecting, which I thought was very interesting. I thought that was just kind of a cool deal. I hadn't really even considered it. Oh, go ahead. Sorry.
No, I just said, keep going. What else?
Oh, yeah. We have a question from a resident young Earth creationist in the chat who wants to ask you, this is a question that they confidently assert you cannot answer. They say, strata have flat, distinct, fine boundaries, and sedimentology experiments prove that strata form rapidly in groups. Explain how you can wedge vast time between them.
Okay. The nature of the changes of the species of animals through geologic time. So take the Grand Canyon, okay? The Grand Canyon sedimentary layering is identified by the fossils that are there that are broken down into time windows. So for example, in the Grand Canyon itself, I'll just even pull the map here and show examples. Right inside the back cover. Where can I get it? Let's see here. Those white bands that white right in there, that is missing. That particular the Ordovician and Silurian time windows are missing completely. No fossils.
Right.
Zip. So that was the time of erosion. It wasn't a time of deposition.
Yep. Yeah.
And back on about page, I think it's about 100. There are about 15 unconformities identified in that whole sequence up through the Grand Canyon.
Yeah, it's I know this particular guy that, well, he's not super keen on answers that do answer the question. So we'll go ahead and move on, because Jonathan is chatting.
You can share my email with him if you'd care to. That's fine.
Yeah, I imagine that would potentially not be a fruitful conversation, but Nephi, if you would like Ken's email, please let me know, and you guys are free to have
I'm just making an offer or a telephone call.
Yeah, sure. Okay, this is a very interesting. I'd be very keen to know the answer to this one. Scott Duke wants to ask you, what geology mystery or unknown would you like to see resolved in your lifetime?
Whoa.
It's a good question.
It is. It is. I'm somewhat at a disadvantage on that in asking that question, partially because I'm not right in the middle of I'm not personally doing active present research.
Right.
Okay. My role in the last 15 years has heavily been, teaching. Teaching things that we know well.
Right.
Well, I'm not too much on the front end. Probably one that I would like to see better resolved, let's say, would be the demise of the dinosaurs. There's still controversy between Chicxulub as an asteroid impact that hit the Yucatan and the huge volcanics that were spilled out on the India subcontinent at about the same time period that carried apparently quite a bit of mercury.
The Deccan traps, yeah.
The Deccan traps, yeah. So that would, and that one might not ever be completely resolved, but that would be one that would be, sort of interesting.
I think I actually read a book that I shill for very frequently on this channel because I think it's so interesting, is The Ends of the World by Peter Brandon. And he covers exactly that controversy because the timing is so odd there. One proposal that I thought was very interesting is this idea that because the Chicxulub impact would have been so powerful in its just velocity, how it smacks into the earth, that it would have actually triggered quite a bit of tectonic activity across the globe. 9 Richter earthquakes and global tidal waves and all this wild stuff that is indeed corroborated at each of these locations. So maybe it could have triggered some of the activity at the Deccan traps was something that was proposed, but I haven't followed up on it. I don't know if that's been booted out of the realm of conversation or not, but I like to imagine these poor dinosaurs that managed to make it through the Chicxulub impact then have to contend with the Deccan traps just going off over in the east, which would have been brutal to say the least.
Probably understanding more about the interior of the Earth would be, geophysicists know a lot, but there'll be continued learning. And sometimes things come up that we don't expect.
Yeah, absolutely.
One of the most interesting ones that I've read about recently is that in southwestern, I believe it's North Dakota or South Dakota, I forget which, there was a location that was found that is interpreted of a incredible tidal wave sweeping up a valley in such catastrophic events. They think it actually happened because of the earthquake, because of the tsunamis formed basically from the asteroid impact 66 million years ago that affected something in South Dakota such that fine ash is actually trapped in the gills of some fish. I mean,
oh wow.
and they make an interpretation that this was not the tidal wave from the Yucatan, but it was because of the rock caused a tsunami type flooding in a river valley way up in North Dakota.
That's so wild. It always kind of, I did a video very recently on impact events, and I was both scared and in awe of how many times the Earth is hit by meteoroids and asteroids, but how many times it's been hit by pretty big ones over the course of the history of the planet. Oh, yeah. And how the one that kind of nerfed the dinosaurs is pretty much the most recent big one, at least of that size. But that you can go around and look at, I believe there's one in South Africa. I can't remember the name of it, but it's this monstrous crater. You might know it. I don't. It starts with a V.
The significant ones that I remember off the top of my head here in the U.S., there's one deep in the Anadarko Basin that was found by petroleum geologists.
Right.
There is one underneath the Chesapeake Bay that's been discovered.
Yeah. I've heard of that one.
Yeah. There's Chicxulub. The biggest one is somewhere over in Russia, in Siberia, is the biggest one.
Yeah. I think they're so cool, but it always kind of wigs me out a little when I look at like the Earth Impact Database, and they're like, oh yeah, meteorite of this size, or meteoroid rather, of this size should strike the Earth every X amount. I'm like, oh,
yeah.
Ooh. That's kind of, the good news is most of the time they just land in the ocean, but still kind of like, it's kind of scary. Okay, let me see what else we've got here. Okay, looks like we have another, it looks like we have another young Earth creationist in the chat wanting to ask some questions. Hello, George Bond. You're welcome to ask Ken any questions if you'd like. Actually, that reminds me. Ken, I'm curious, are there any geologists out there that you know of who are proposing that the Chicxulub crater was created by anything other than an impact event?
Well, not practicing geologists. There are some arguments that come from young Earth creationists that it may not have been.
Gotcha.
That would be, be very, very minor. I mean, it's not appropriate to say that there is no geologist anywhere that doesn't. That you can't know for sure.
Right. I was just curious. I had that conversation with this individual a while back, and I had said something quite similar. Orgay.
The thing about Chicxulub, unlike when I was in my teaching years, now within the last 10 years, they've actually taken drilling. They've drilled down, and they physically have the busted up pieces of rock that were right down in the core of that. It's called a breccia. It just broken up rock completely. So it's a lithology that's very complex that basically was derived from that catastrophic event.
Right.
It's not ordinary sediment.
Right. Yeah. There. One thing too that I've tend to bring up that a lot of folks do bring up, but it's the iridium layer in combination with like shocked quartz, the nature of the tectites that we find, just the morphometry of the entire location that lends itself to something that has to be a large impact extraterrestrial.
There are some people that are telling church folks that there's no iridium actually found down in the Chicxulub crater, and I don't know. I've not tried to look that up because the iridium layer, the data that I've seen come from Italy at that KT boundary or KPG boundary.
Right.
And I've seen the data, and I have the data in my files from a location in Colorado. And the location in Colorado the iridium increase was like 4 orders of magnitude.
Right. Yeah. Yeah. In some places, when I was doing some research for this video, some places too, it's higher than that. It's wild how high that, like, as far as background iridium.
Yeah.
I wanted to ask a question from Orge. This is a fun one. Orge wants to know what your favorite geological period is.
Probably the Pleistocene, all these glacial periods.
Yeah.
I haven't thought of it that way, but I heard somebody else describe it that they did feel they had a favorite period. That hasn't been my thinking process. That's just off the cuff.
We ran into the same problem with Jonathan when he was on. He was like, I never really thought of what's my favorit period. It's
yeah. See, I never have.
Yeah, it's very that's hilarious. I'm a little biased because I study primates, but I have like, which ones are fun to watch and which ones have a lot of good data on them versus which ones are the cutest or the smartest or whatever. So it's like, you ask me my favorite primate, it depends on the category. So I would imagine it would be the same for geology, but Orge says, good answer. They are all exciting.
I guess if I worked for an oil company that was working the Permian Basin, then I would just say, Permian.
Yeah, the Permian. The Permian also blew my. Looking into the Permian and the mass extinction that caps it off is mind-blowing. It's so cool. Well, let me see if we've got any other questions going on here in the side chat. Mostly it's our friends.
I see Jonathan Baker's in there too. Looks at it.
Yeah, Jonathan Baker's hanging out. Jonathan has been helping field some of the questions from our Young Earth Creationist friends in the side chat, which is good, which is very good. Let me see here. I think we've covered all of the questions. I have one more for you. I think I was asked this the other day, and I wanted to have a succinct way of explaining it that I think you would definitely be better at than I. Suppose you had a rock sample that you dated using potassium argon or argon, something with a generally wide range of dates that it can cover.
Yeah.
I was actually having this conversation with the Young Earth Creationists. They wanted to know if you were to actually get a date that was outside of the range that it could cover, like let's say you inappropriately dated something very young with something that is outside of that dating range.
Yeah.
What answer would you get, and how would you know it was incorrect without having any background knowledge of the rock?
Okay. You don't date rocks without knowing where they're from.
Okay.
There's no point.
Yeah.
Okay. It has to get an age. You need to have a geological environment, know something about that setting, and if there are outliers, there may be some good reasons there are outliers.
Right.
Okay. One of the things I find very annoying is that Young Earth Creationists, they just randomly make a claim if it doesn't fit what they believe. Well, you don't know you don't know the answer until you've done a whole bunch of data. Okay. Yeah. If you have 100 analyses that tell one answer and there's one outline, something happened in the laboratory.
Yeah.
So that's part of doing research. That's inevitable laboratory work.
Well, and there's the factor of statistical significance, right? It's like if you have 5 tests that give you one answer and then an outlier, is it possible that the outlier is perhaps impacted by factors that were not taken into account or that we don't understand? That kind of thing.
Yeah, we may never know.
It doesn't tend to come into play. Yeah. One of our Young Earth Creationist friends has a question for you. They want to know, hold on, I don't want to put words into their mouth. I'm trying to find their exact chat here. Question for Ken. And this is quite vague, so I will try to help knowing this individual what perhaps they mean. Their question is straight up, how do you explain erosion rates? This individual in the past has presented papers from the 1980s, etc., showing erosion rates in given locations and proposing that because erosion rates are so fast, certain structures should no longer exist. In the past, I have suggested that deposition is not being taken into account. But George, if you would like to kind of elaborate on your question for Ken, feel free in the side chat. And I guess you can answer that how you will, Ken, with the information we have so far.
Well, a most common, or one of the common comments is made, if erosion takes place on the continents, all the continents should be down to sea level.
Right.
Okay. If the Earth were 1 billion years old. Well, the Himalaya mountains at 29,000 feet, the highest mountains in the world, have just been constructed by plate tectonics in the last 10 to 20 million years. So the erosion rate, the early Earth was covered with water, and it was after some tens or hundreds of millions of years before the interior of the Earth segregated out into a molten core and got convection happening in the mantle that eventually began to produce dry land, right? Basically, day 3 of Genesis, if you will. And through about 1 billion years of history, there was not much land. There were not much in the terms of area of continents. Then over about the next billion years, gradually a lot more plate tectonics happened, causing the continents that were small originally to get bigger and bigger and bigger until today we have about 30% of the surface area of the Earth has continents. So that's a long continuous process, but it's still going on.
That kind of thing kind of makes me wonder. They've clarified and say that they're not referring to isolations, but major rivers of the world. And to me, that, if I may, that runs into the same problem as what we were just discussing now, which is areas of Earth, thanks to the tectonic and geologic activity of the planet, aren't static. They're constantly in flux. Now, in geologic time, this is happening quite slowly, or to us, rather, it's happening quite slowly, but rivers don't continuously flow in the same place. They wind, they change locations because of the Earth below them. The very Earth beneath them is shifting in and of itself. So I guess I'm not really sure. I've never been sure, interacting with this individual, what the problem being proposed is. They say now they are your own, I suppose, referring to conventional science's erosion rates, should erode in 40 to 50 million years. But again, this accounts not for uplift or any kind of tectonic activity.
Yeah, so the Earth is dynamic. So.
Yeah, I don't understand, and okay, sorry, George. I don't know how to answer your question other than just saying yes. The Earth, like what Ken just said, the Earth is in fact dynamic. At the small scale and at the large too. But you know, I don't know how much more clear.
The individuals that do study erosion rates are those that pay a lot of attention to sort of an individual basin. They're seeking to find out, how fast is this eroding down?
Sure. Yeah.
And that's part of, but it will vary a lot. Once the land gets really flat, then erosion rates will be very slow. Erosion rates can be higher when there's more terrain because the rain is moving faster down slope to carry sedimentary material, broken up rocks down slope toward the oceans.
Right. Yeah, absolutely. Well, I think that's all our questions. This has been just incredibly enjoyable for me, and I know everyone in the chat has been having a blast. We've had a ton of people come in and cycle through, and we've just had
Thank you very much for the opportunity.
Oh my gosh, listen.
It's my joy, the privilege to be able to share what I've learned about God's creation through this lens of geology and geochemistry, and particularly share it with the church and people want to know, what is a truthful description of the earth.
Well, and I think, yeah, and and you and I have discussed this before, Ken, but oh, I'm so sorry, I did miss one question. Thank you, Orvami Swami, for bringing that to my attention. They wanted to ask, I know the answer to this because it's covered in Grand Canyon Monument, actually one of your chapters, Ken, but they wanted to ask you what your thoughts are on the problem for young Earth creationism with regard to excess amounts of heat.
Excessive amounts of heat where?
Just in general, how to cram heat into a 6,000-year time span if you're dealing with accelerating radioactive decay or moving the continents around really quickly, things of that nature.
Yeah, that's really basic evidence that the Earth is ancient. That's what it amounts to.
Yeah.
I listened to the speaker that invented the catastrophic plate tectonics. And he just straight up at the end of his talk just said, heat's a problem because the Earth should be molten.
Yeah. Yeah.
And he ultimately said, I just believe God miraculously cooled everything down.
Yeah, I've heard the same. And one thing that I do appreciate when individuals like that are transparent about that, saying, look, appealing to this kind of miraculous intervention is something able. And you and I discussed this in a phone call. I don't think that that's consistent with God's nature. If you're having the proper exegesis of the Bible, I don't think that it would be inherently deceitful. In kind of doing these kinds of look really ancient, but actually it's not.
That needs to be addressed, and that's part of the problem. Okay.
Yeah.
Because God did the miraculous through people, and when people were there on Earth, that's where the miraculous things happen. Yeah. And in Genesis 1:1, when everything was created at the time of the Big Bang. So.
I know folks. I've talked to folks who are Christians and those who are not, and neither seems to accept that a proper exegesis is a young Earth one. Interestingly enough, even people who have a horse in the race don't think that. Which is interesting. But I'm so sorry. Thank you for answering all the questions, and I'm so sorry if we're 2 minutes over the limit. I don't want to hold you longer than 2 hours, but I really want to talk about this.
Again, just appreciate the opportunity, and whenever it's time for me to come on again with your team, and we have a topic, might want to dig in deeper with radiometric dating, or dig into Grand Canyon, some of the issues there.
I know everyone would be very interested in a Grand Canyon deep dive. Everyone loves the Grand Canyon because it's such it's first of all, it's just cool. It's just a really cool structure. All of the layers are there in full display. And it's an amazing structure. But it's such a superb representation of how ancient our planet is and how empowering and beautiful that is as a fact of our life. So thank you everyone for watching, and again
thank you. I don't know how many are there, but thanks to all of you.
Yeah, we got about 60 people right now.
What's that?
We've got about 60 people right now watching.
Oh, wonderful. Good.
So they will very psyched. So I will end the broadcast, and then Ken, you and I will still be in the back room, so we'll sign up there as well. Okay. Thank you everyone. Bye-bye.
Thank you. Bye.